So every time you sit down to stream a movie, save a massive file to the cloud, or, run some complex AI model, you're relying on something you probably never even think about: electricity. Welcome to The Explainer. Today, we're looking at the incredible, massive, completely hidden electrical infrastructure that's actually keeping our digital world alive. We're talking about a highly engineered, hidden fortress of copper, lithium, and diesel, designed to deliver one thing above absolutely all else: continuous power.
Which really begs the question, right? What keeps the internet from going dark? I mean, think about it. If your house loses power for a second, the lights flicker, you reset your microwave clock, and it's really no big deal. But if a data center loses power for even a fraction of a second, oh man, the stakes are absolutely astronomical.
We're talking about just seconds of downtime, literally shutting down thousands of servers, interrupting global business operations, and costing millions of dollars in a matter of heartbeats. It is an absolute existential threat to the digital services we rely on every single second of the day. Okay, let's dive into this and see exactly how these facilities are engineered to prevent that nightmare scenario from ever happening.
To really understand this infrastructure, we're going to break down three key concepts today. First, distributing high voltage power. Second, instant backup systems. And third, designing for redundancy.
All right, let's jump into concept number one: distributing high voltage power. So, taking a macro to micro approach, we've got to start at the very beginning, the moment electricity arrives from the utility grid. And it comes in at an absolutely massive scale, often between 13,000 and 35,000 volts. Data centers have an enormous, constant power demand, and that raw influx of power, it's enough to literally vaporize sensitive electronics. It is way, way too much voltage for a server to handle directly. Let's move to and see how this builds, because to handle that massive voltage, the power path inside a data center is essentially just a series of really carefully controlled voltage transformations. The power steps down safely in stages. Starting from the utility grid, it moves into the switchgear, then through step-down transformers, into power distribution units, or PDUs, and finally it flows through branch circuits and rack power strips directly into the servers. You can kind of think of the switchgear as a high-tech traffic control center for all that incoming electricity. It is, hands down, one of the most important pieces of equipment in the entire building. It safely manages that initial massive influx of power, which allows the facility operators to isolate circuits, redirect power flows, and basically protect the whole system using these heavy-duty breakers and relays. And then, right after the switchgear, step-down transformers drop that intense high voltage down to a much more manageable 480 volts. From there, that 480-volt power hits the power distribution unit, or PDU. And this is the final major translation step. The PDU takes that 480-volt power and converts it down one last time, usually to the 208 or 120 volts that are actually used by the server equipment itself. From here, the power travels safely through those branch circuits and goes right into the server racks.
Moving on to section 2, instant backup systems.
Now, simply distributing power isn't enough, right? Because as we said earlier, even a momentary outage is completely catastrophic. So to prevent even a tiny blip, data centers rely on an uninterruptible power supply, or UPS. And honestly, I find this part absolutely fascinating. These things act like massive electrical batteries. When utility power is flowing normally from the grid, the UPS is actively conditioning and stabilizing the electricity before it hits the servers. But if that utility power suddenly fails, boom, the UPS instantly switches to battery power. And I mean literally instantly. It catches the system so fast that the sensitive servers never even notice a drop in voltage. Now, what's really interesting about this slide is the deep contrast between our backup layers. The UPS is incredible because of its instant transition, but it has a fundamentally short duration. It's battery-powered and really just meant to hold the fort. Contrast that with the backup generators, which can take up to 60 seconds to automatically start and reach full output. But they offer a long-term duration because they're fueled by heavy-duty diesel engines. To really grasp how clever this layered approach is, let's walk through the exact high-stakes chronological sequence of a power outage. Okay, at 0 seconds, the utility grid fails. The lights go out in the whole neighborhood. At exactly 1 second, those massive UPS batteries have already instantly taken over, keeping the servers perfectly humming. This gives the facility the absolutely crucial runway it needs. Over the next minute, those massive diesel engines outside start firing up, and by 60 seconds, the diesel generators reach full output, seamlessly taking the heavy electrical load over from the UPS batteries. It is a perfectly choreographed handoff. And just to be clear, these aren't your typical noisy home generators.
We're talking about massive industrial engines producing several megawatts of power. They literally sound like a jet engine when they spin up. These backup generators can run for days as long as fuel deliveries keep coming. In fact, some facilities store enough fuel right on site to operate for many hours or even several days, keeping the internet running flawlessly during major, prolonged utility grid outages. Which brings us to Section 3, Designing for Redundancy. All of this amazing equipment we just talked about means absolutely nothing if there is a single point of failure in the chain. Redundancy is the ultimate safety net. Basically, it means duplicating everything. Instead of relying on a single piece of equipment, data centers use redundancy strategies like duplicate utility feeds, literally bringing power in from two entirely different utility grid substations. They install multiple UPS systems, multiple backup generators, and sometimes even completely duplicated electrical distribution paths. You'll often hear these high-reliability engineering strategies referred to with terms like N+1, or 2N design concepts. Ultimately, it ensures that whether a piece of equipment unexpectedly fails or, just needs to be taken offline for routine maintenance, facility operations are never, ever interrupted.
So the crucial point is that the golden rule of this architecture is incredibly simple. No single failure should ever take down the data center. Because of this extreme intentional duplication, combined with the layered power distribution and the instant backups we just explored, data centers truly represent some of the most reliable electrical systems ever built on Earth.
I absolutely love this quote because it really just sums it all up perfectly. While the flashing servers and the massive cooling systems usually get all the attention, the electrical infrastructure is what actually makes the entire facility possible. Without it, the internet as we know it simply would not exist. Without this invisible fortress of highly engineered electricity, tens of thousands of advanced servers are basically just heavy, useless metal boxes. So, next time you load a web page, stream a video, or save a photo to the cloud, ask yourself, how many layers of hidden power are currently working together to keep your screen lit? It is pretty fascinating to think about all the incredible engineering happening right now, completely out of sight, just to make that happen. Thanks for tuning into this explainer. Next time, we're going to dive even deeper and take a closer look at exactly how those critical UPS battery systems work to maintain uninterrupted operations. See you then!